O- Okay, so in chapter 11, I'm going to talk about gravity and planetary orbit, which is about Kepler's law, three laws, and the hydrogen atom. So, I'll go somewhat slowly. Every particle in the universe attracts, okay, that is the discovery of Newton, every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, so this is the celebrated Newton's gravitational attraction. So here is m is mass, r is the distance between these two particles, and g is the universal gravitational constant. It's constant. It does not depend on on the situation you measure this force. It's just constant, and that is given 6.674 times 10 to the minus 11. Okay, so this is very small number. 10 to the minus 11 is a very small number. So if this force is very small between, for example, small masses. So this force can be felt when at least one of them is very large, like the mass of the, for example, uh, Earth. Okay, so on the surface of the Earth, we just feel this gravitational force because the mass of the Earth is very large. So after Newton's proposal, it was measured actually. This gravitational force was measured, and G was determined by uh, Henry Cavendish in 1789. Okay, so here is how he measured this one. Okay, so you first locate a. This is initial. The 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 dashed line is initial position of these two particles here. Okay, so originally it was these particles were placed here, and then you bring a very large mass near this one. Okay, then they'll attract. Okay, and this attraction will twist this mirror, and the light will be diffracted. Okay, so you can see the difference between uh, before bringing this mass and then after bringing this mass, the light will be deflected. Okay, so this apparatus shown allow the attractive force between two spheres to cause the, this rod to rotate. Okay, and then this mirror amplifies the motion, and you can if you can calculate the difference of this, then you can determine G. If you know the mass of this one, and just using this formula, okay, and G can be determined. So it was repeated for various masses, and this was actually this was accurately determined to be this value here. Okay, this value. So it's just remarkable that this type of experiment could be performed at these early times. Okay, just even before the 1800 years. this is an example of inverse square law. Of course, there are other inverse square laws. For example, in the second semester, we are going to study Coulomb's law, which is also inverse square law. And gravitation is just an example of inverse square law. The magnitude of the force varies as the inverse square of the separation and division. Okay. So you may wonder why is it r squared here? Okay, why isn't it like r cubed or 1 over r, or why isn't it like 1 over 1.5 here? Okay. Well, if somebody asks you that, then you can just answer in a very simple way. Why is Newton's law 1 over r squared? Okay, then you can just simply answer by following. Okay, ask the man who asked this question, what is the surface area of the sphere? What is the surface area of the sphere? That is, we know 4 pi r squared here. Okay, this is r squared. And this r squared and this r squared are very closely related. And the reason that Newton's law is 1 over r squared is just equivalent to saying that the surface of the area is r squared. Okay, so that 1 over r squared times this 1 over r squared times 4 pi is just 4 pi. Okay, so it has to be r squared because we know that the surface area of a sphere has to be 4 pi r squared. Okay, so that is one answer. If you study the advanced physics, this will become clear, but at this level you can just say, why is it 1 over r squared? Well, because the area of the surface is 4 pi r squared. And in vector form, it is written in this way. So this needs some explanation. We have one particle 1 here, and particle 2 here, and this the distance from this 1, 2 means vector from r1, 2. Okay, so this notation means that this is the force acting on particle 2 by the presence of particle 1. Okay, so this is particle force acting on particle 2. This is our notation. So you can just, it is usually written as 1, 2, and that means here the particle 2 will be, the force will be in this direction. Okay, and g m1 m2 square r1 2, and now this is the magnitude of the force, and direction here, you see direction r1 2 is unit vector. Hat usually means unit vector. We call ijk, or carries hat, which has magnitude 1. So this one is magnitude 1, and the direction is from 1 to 2. Okay, so r1 to 2 is written as r1 2, which is a unit vector from 1 to 2. Okay, so this is unit vector. So the force actually acting on particle 2 is attracted, therefore you need a minus sign here. Okay, so that is F12 is equal to minus R hat 1 2. Conversely, F21, which is attractive force acting on 1 by the presence of particle 2, should be written as minus G R squared M1 M2 R21. Okay, R21 is unit vector from here, but this is attracted. Okay, Therefore, you should minus here. Or you can just write it as G R squared M1 M2 R2 1. Okay? R2 1 is the vector of this direction. So these are all the same, but usually to emphasize this is an attractive force, you write in this fashion. F12 is R12 and minus here. Okay, so this minus sign is just the existence of this force, attractive existence of attractive force. Okay, attractive nature of this force. And obviously, this one, in this system, the total force is 0 because F12 acting on 2 and F21 acting on 1 is 0. Okay? So that is a better expression of this force. So here again, I explained this, but here again, F12 is force exerted by particle 1 on particle 2. Okay, so 2 comes last. The negative sign in vector form of the equation indicates the particle 2 is attracted toward particle 1. F21 is a force exerted on particle 2 on particle 1. Okay, and that is minus of this one. So F12 plus F21 is 0. So if you consider these two as an isolated system, the sum of total internal force is 0. Okay, so once again, just to remind you, F12 is equal to minus G, Newton's constant, R squared over M1, M2, R1, 2. Okay, the minus here indicates the attractive nature of the force. And another basic fact we need to discuss the gravitation is that gravitational force exerted by a finite sized spherically symmetric mass distribution on a particle outside the distribution is the same as if the entire mass of the distribution were concentrated at its center. So we are going to consider most of the cases this spherically solid mass distribution with mass m. So whenever you consider this, consider the gravitation of this with some other particle, you can just think of this, all the mass concentrated here at the center of mass, okay? And if this is R, then F is just equal to G R squared over mm, okay? So for a spherical distribution of mass, the gravitational effect is the same if you just consider all the masses are concentrated at the center, okay? That is just one basic knowledge we're going to use throughout this lecture. Okay, so you can prove it, but let's just skip this because it's very complicated, tricky mathematical integration is involved. So you'll just take it as a fact that whenever there is spherical distribution of mass, then you can always treat that as the mass concentrated at the center. Gravitation is a field force that always exists between two particles, regardless of the medium between them. Okay, and the force decreases rapidly as the distance increases. Okay, so this is a consequence of the inverse square law because it's proportional to 1 over r squared. And this field force, remember, there is when we discuss this Newton's law, there are two classes of force. One was contact force, that the force existing between particles that are in contact with each other, and field force that can exist when they are separated far, and there is no need to be contact or to have contact, or just that there's no need to have any medium, and gravitational force is a field force, okay? Field force here. So it doesn't always have to be in contact, or you don't need any medium. Use the mental representation of a field. So let's look at this. What is the field force in bit detail? A source mass creates a gravitational field throughout the space around it, and test mass located in the field experience gravitational force. Okay, so you may ask, if there is no contact between these two particles, okay, then how does he know that this? How does he, know that there is a particle M that he is attracted? So how does, let me put it in this way, how is the force exist here between these two particles? How do you describe this gravitational force which is not in contact? Okay, so the correct way of saying is this: if there is mass m here, it creates some kind of field in space, okay? And then this field interact with this mass, okay? And this gravitational field G is the unit force of this one. Gravitational, this field is a unit, is vector field is a unit for force for unit mass. Okay, so this is how you can describe this field force. Okay, so a source mass creates a gravitational field throughout the space. So whenever there is a mass here, it creates a gravitational field. Okay, and if you located a test particle in this field, it will experience this gravitational force through this gravitational field. Okay, and the gravitational field now is defined as G is Fg over m. Okay, so this is not just a way of thinking about it. It actually creates gravitational field. Okay, how can I see that? Suppose mass m is here. Okay, so I locate the test particle. Suppose I perturb this one. Okay, then this gravitational field actually perturbs, and that effect is transmitted to this one. So okay, so this particle, if there is perturbation, this particle can detect this perturbation through this propagation of the gravitational wave field, and in that case, this propagating gravitational field is called gravitational wave. Okay, actually this gravitational wave was detected in the last year, and it was Einstein actually predicted this gravitational wave around 1917, and after almost more than 100 years, this gravitational wave has actually been detected. Okay, so this is not just a way of describing it. If the existence of the gravitational field is real, Okay? If you perturb this, then this perturbation can creates a gravitational wave, and that affects this mass m here. Okay? And the gravitational field is defined in Newton's case. It's defined as the force per unit mass, but actually in Einstein theory you have to define different way. But anyhow, they are basically the same. So remember that if there is a mass here, it creates actually in reality a field called gravitational field, and if this is perturbed, then the perturbation propagates through the space in the form of wave, and that is called gravitational wave. And this gravitational wave has been detected recently. So G now can be written as this one, okay? And we know Fg was equal to R square over. So here, mass m, R hat is unit vector from 1 to 2. So this is a force that is acting on this particle. Okay, so this one was 2 in our notation. So R hat was from 1 to 2. Okay, and minus is just represents the attractive nature of the gravitational force. And so G, which was defined as the force, gravitational force per unit mass, is now given by minus GME over R square R hat. Okay, and if we, at the surface of the Earth, G is this familiar 9.80 meter per second. So gravitational field exists in reality, okay, and a gravitational field vector in the vicinity of uniform spherical mass looks like this. Because gravitational field is defined as mass of mg, okay, so this one and this has the same direction, fg, so it attractive, and this the length becomes the magnitude of the vector field becomes larger because because of this vector 1 over r squared. This is proportional to 1 over r squared. Near the surface of it, the g is constant, so it's constant. Okay, so force is always, so if the gravitational field is given like this, if you place a particle here, then it will just accelerate along this direction. If you place a particle here, this is the direction is the same, so this is direction of the force, and we can accelerate like this. So this is near the surface of the Earth, and this is in general how the gravitational field is aligned. So here, using the known radius of the Earth and the g is equal to 9.80 at the Earth's surface, find the average density of the Earth. Okay, so it's just the standard way. So ME is given by this. Okay, that was just the mass of the Earth. Let's see. Mg is equal to M R E squared over, I'm sorry, G N M M. So this cancels. So ME is equal to G R E squared over G. So that is this one. And then we know that the density of the row density is the mass per unit the mass per unit volume. So this one and this one, and rho E is given by this, and you can just plug in the numbers here. G is 9.8 and Re is this one, so the density is it's like ton. One ton is about 10 to 3 kilograms. So 1 ton per cubic meters. Okay, so I'm sorry. So basically, this is just the density of the rock. Okay, the Earth is mainly consists of rocks, and I mean at least in the surface. Now let's go to Kepler's. So Kepler's law was discovered even before Newton's law, but by just pure observation and measurement, and Newton was able to actually rederive Kepler's law using the inverse square law. So Kepler didn't know this gravitational force, but actually Newton found out that all these Kepler's laws are the result of this gravitational force. Okay, so Kepler was a German astronomer. He was a Tycho Brahe's assistant. Brahe was the last of the naked eye observers. So it's amazing that this Brahe measured all this data with his naked eye without using any telescope and things like that. And then Kepler reinterpreted this data and formulated these three laws of all planetary motion. Again, these are all just natural consequence of this gravitational force of gravitational attraction, but Kepler didn't realize it, just he formulated it, announced it in the three laws. So what is first law? The first law is all planets move in an elliptical orbit with the sun at one focus. Okay, so let's talk about what is ellipse. So elliptic orbit in mathematics is defined as some curve that has 2 points, special points called focus. Okay, so it's foci, two forces, and this one is special that the curve is trajectory satisfying the following condition: R1 and R2. R1 is a distance measured from one focus, and R2 is distance measured from the other focus, is a constant. Okay, so this remains constant. It means that it generates a curve called ellipse. Okay, ellipse. And it also has other special point, which is called a center here. And the long distance through the center is called the major axis. Okay, and distance from the center to this point here is called semi-major axis. And semi-major axis has length A, and this one is called semi-minor axis, has length B, and each focus is located at a distance C. So C is the distance from the center of the ellipse to the focus, and they are the same, they are symmetric. So here is also C, it's also C. The shortest I mean, sorry, here again, just repeating. The shortest distance through the center is a semi-major axis, semi-minor axis. And the eccentricity, you see, this looks like sphere, but it could squeeze more like this. And how much this squeezing occurs is determined by the eccentricity. It's defined as C over A. Okay? C over A. For a circle, eccentricity is 0. So this one is not squeezed. Okay, so C equals 0 means that the two focal points just coincide, and that just becomes center. So all these focal points and center are at the same point here, and that is circle. Then there's no squeezing, and the eccentricity is 0. But if this one is very much squeezed like this, okay, then eccentricity increases. Okay, and E actually cannot be larger than 1. So if E is equal to 1, looks like very squeezed like this flying saucer. So I just summarize what you have just said. C is the distance from the center to either focal points. B is a semi-minor axis. A is a semi-major axis. And suppose, I mean, the Earth, every planet around the sun is undergoing a elliptical motion, and sun is located at one focus here. Here there's nothing. Okay, the sun is located at one focus, and the nearest point that the planet approaches is called perihelion, and the furthest point from the sun is called aphelion. Okay, so here you see the geometry tells you the distance of A plus distance from the sun to the aphelion is C plus A, and distance from the sun to the perihelion is A, this one is A minus C, so this distance. And here R1 plus now R1, the constant that determines is what? This is a constant, so you can choose arbitrary point here. So let's pick up this point or this point for convenience. What is R1 plus R2? R1 is this one, which is A minus C. R2 is this, the distance measured from this point is what? This is this plus this. Okay, so this A plus C. So A plus C. So it's 2A. So the constant that I mentioned, which characterize one ellipse, is given by 2 times the semi-major axis. Okay, that is constant. The constant. The sun is at one focus. Nothing is located at the other focus. Aphelion is the point is furthest away from the sun. The distance is A plus C. Perihelion is point nearest to the sun, and distance is minus AC. Okay. For a particular orbit of the Earth, this perihelion is called perigee. Okay, and aphelion is called apogee. Okay, so this is just two names that just apply to Earth, and for general orbit it's called aphelion and perihelion. A circular orbit is a special case of general electric orbit. Okay, so this one is C is equal to 0, or eccentricity is equal to 0. Okay, and this is a direct result of inverse square root nature of the gravitational force. Okay, just don't be confused. The gravitational inverse square root does not only make circular orbit, it can also make elliptical orbit, and that all a result of this inverse square law. And in particular, elliptical and circular orbits are bounded objects. Okay, they cannot go to infinity. Okay, so that is called bounded object. And a bound object repeatedly orbits the center. Okay, that is bounded motion, so it repeats itself. So it means it has some periodicity. Okay, so for example, for Earth, it is 1 year. After 1 year, it just repeats itself. And there is also unbounded object that will pass by and will never return. And this object could have passes that are parabolas and hyperbolas. Okay? So the most general motion can be either bounded motion or parabolic motion or hyperbolic motion. So for just give just one example, it could be either elliptic or parabolic motion like this. So this particle is moving very fast, so it is attracted, but it will just pass away and will never return. And hyperbola is also the same. Okay, just comes here and goes like that. And there's a difference between this one, but I'm not going to. So just remember, this one is unbounded object. Okay, and bounded object undergoes the elliptic motion. So Mercury has the highest eccentricity of any planet, it turns out. So it has most, as far as planets concerned, the Mercury has the highest 0.01. Halley's Comet has an orbit with high eccentricity. I don't know whether you have heard about this comet, but it has passed in the last century. I see it has passed through the center, so it will take a very long. Oh, sorry, it has passed through Sun in the last century, and it will take a very long time when it comes back. Okay, the Mercury also has some very high eccentricity. The Earth's eccentricity is almost zero, so it means that the Earth, we can safely regard the Earth's motion as a central motion around the Sun. Okay, it's a very small number, 0.0167. Now, the Kepler second law is the radius vector drawn from the Sun to any planet shifts out equal areas in equal time intervals. Okay, so this is also can be derived from, actually in this case, it can be derived from the momentum conservation. Okay, so Sun and the planet are an isolated system, and the total momentum, the angular momentum must be conserved. So, recall that L is equal to R cross P, which is MP R cross V. Okay, so if you consider an orbit, this one is R, this one is dr, which is v dt. Okay, so L is conserved. So let's see what does it mean by how can we apply this L conserved to this situation here. Okay, so first, during a delta dt, since v is the velocity here, it will shift out how much? R cross dr. Okay, that is the area. Let's call it just magnitude of this. Okay, the area swept out during time dt. Okay, so that is equal to r cross v. Dr is v dt. Okay, so dt is constant, so you can just put it like that. Okay, now you see dt over dA, so the area swept out per unit time is what? Is equal to, sorry, let's go here. The area swept out per unit time is equal to R cross V. Now, this one, I can write it, multiply this M here and divide by 1 over M here, so I can write it 1 over M R cross MV. Okay? Okay. So this one becomes 1 over M and R cross P. Okay, that is precisely the angular momentum, which is a constant, because M is constant, it is constant. So the area swept out during the delta time is a constant. So this area is constant. So it means the plane is moving at this position and at this position during delta time t, the area are all the same. Here, the velocity is very fast, so looks like they're all the same. The area during delta per unit time, they're all the same. Okay, so I have just proved that we did geometrically in a time dt, the radius vector sweeps out the area dA, which is half the area of the parallelogram. Okay. So I haven't actually, there's one missing link here. So how do I know that I just assume dA area was equal to R times dr. Okay, where dr was equal to v dt. So how do I know this is the area? Okay, so you can just say, it's very easy actually. So you have, suppose you have R and dr. Okay, so what is the area of this? So I want to show that this is the area of this. Area of the, I mean this one is the area of this. Okay, so how do I know that? Well, it's just clear from this, the meaning of this one. Let's see. Let me just, it can be shown very easily actually. So let's insert a blank page here. So suppose you have A cross B. Okay, so here A is equal to R. For example, B is equal to dr. It doesn't matter which vector, but any given A2 vector. So what is the meaning of, geometrical meaning of A cross B? Actually, I should have explained this when it's defined this one, but anyhow, it's time. So you have A, and suppose you have B vector here. So what is A cross B? Geometrical meaning of A cross B. We know that A cross B magnitude is equal to A B sine theta, which is theta here. Okay, so A cross B, suppose I make a parallel rectangle here. Okay, so what is A B sine theta? We know that the area of this parallel rectangle, if the length of this is AB, and if this angle is theta, then this one is B sine theta, and we know that the area of this is equal to AB sine theta. okay, which is precisely the A cross B. So A cross B is the magnitude is actually the area of a rectangle, parallel rectangle, created by A at its one side and B at the other side. So here R cross dr, which is equal to V dt. So this area is the half of the area created by R times dr. Okay, because it has this side here. So this is half, and that was this one was angular momentum. So the area is twice the area swept out during unit per unit time is twice the angular momentum. Okay, so that should be clear. So area is 1/2. Okay, so area R cross dr, and the area, total area is R cross dr. I just proved, and we are interested in this area. The area swept out per unit time is 1/2 of this one. Okay, and that is, if we are divided by this, that is the area swept out per unit time. Okay, so I missed this to half, but anyhow, R cross dr is the area, and this area that is swept out by this planet is on. You should all count this half of it. Okay, so the radius vector from the sun to any planet sweeps out equal areas in equal times. Okay, so it means that let's draw a big diagram here. Okay, suppose you have a sun, the earth is moving, so it has to sweep out a constant area per unit time. So if the earth is moving like this, it has to move slowly, okay, because it must be the same, this area must be the same when the earth is near it. Okay, so here it has to move very fast because they must have the same area per unit time. Okay, now let's talk about Kepler's third law. So Kepler's third law is the square of the orbital period of any planet is proportional to the cube of the center. So this one says that this is bounded motion, so it has period, let's call it large T, is proportional to the cube of semi-major axis. Okay, so there is always this relation. So how do I prove it? For a general orbit, elliptical orbit, you need more technical knowledge of it. So I will just prove it for a circular orbit, okay, and then just generalize it. So how do I prove that this for a circular orbit? So this undergoing a circular motion, we know that gravitational force is responsible for this centripetal acceleration. Okay, so this one is gravitational force. On the left hand side, you have the gravitational force, and this one is m v square bar. So that one gives immediately this relation. Okay, it's just easy. I'm not this relation where I have used here this m r square over gm is equal to m r over v squared, and they cancel. Okay, and I put v, since this is circular orbit, if this velocity is constant velocity, then the velocity should equal to 2 pi r over the period. Okay, that is the time required to make one complete revolution. And this relation immediately gives you t squared is equal to ksr squared. It is a relation that is proportional to r squared, and that is this one. Okay. Here ks is a constant. Where ks is a constant. Is constant. Okay, so this one is same for, you see, this one only depends on the mass of the Earth, so this one is same for all the orbits. Okay, so that is the relation for the orbit, the circular orbit. And it turns out, if you do a correct computation, the t square for an elliptical orbit is precisely given with the same ks times a cubed, where a is the major axis. So if you do the same computation, which is of course much harder at this level, but anyhow, so do the same orbit with semi-major axis a, you get this relation. Okay, so which is just direct generalization of this result, but ks here is the same. You obtain the same. Okay, that is only depends on the gravitational constant and mass of the sun. Okay, and that is also very small number here. So that is the Kepler's law. So t squared is equal to ksr cubed, and for a general orbit, t squared is ks a cubed. Okay, so here it is written here. This can be extended with elliptic orbit and replace small radius of the circle with the semi-major axis, and it's the same ks but a. So ks is independent of the mass of the planet and is varied for any planet. If an object is orbiting another object, the value of k will depend on the object being orbited. Okay, if for example, if a particle is orbiting around Earth, then ks and k Earth is k Sun is replaced by k Earth. So it means that ks this is for relation that is true for planet orbiting around the Sun, and if you consider a Earth and orbiting mass, then you can use t squared is equal to k Earth a cubed, or in this case r cubed, where r is the distance measured from the center of the Earth, and ke in this case should be 4 pi square over g m e. Okay, I don't know exactly what the number is this, but we'll have a chance to look at this precise number of this ke later. So right now I don't remember exactly what it is. So now let's consider a satellite of mass m moving in a circular orbit around the Earth at a constant speed v and at an altitude height h from the surface, above the Earth's surface. Okay, so this example is called geosynchronous satellite. Okay, synchronous, that is fixed. It maintain its fixed position. Okay, so obviously, in order to be fixed here, it has to rotate the same as the period of the Earth rotation. So it means the period, when this object has a period of 1 day, then it becomes a geosynchronous satellite. Determine the speed of satellite in terms of G, HRE, and ME of the sun. Okay, so speed can be determined, for example, the gravitational force being equal to mv square over r, G, H, and RE. So this is the centripetal acceleration, and the source of that is gravitational force. And then you can solve for V, and noting that the distance r from the center, you just have to be careful. It's h is just height, altitude measured from the Earth. So you always have to consider distance from the center of the Earth. Okay, so V is given like this. Okay, now you can just substitute the numbers. Now, if the satellite is to be geosynchronous, that means that appear to remain over a fixed position on Earth. Okay, we know that Earth is just rotating, and this satellite remains at a fixed point. Suppose this is Korean Peninsula. Okay, and then it just remains here, but this one is rotating, so it has to rotate. So it means that this one has to rotate with a period of 1 day. Okay, so if the satellite is to be geosynchronous, that is appearing to remain over a fixed position on Earth, how fast is it moving through the space? Okay, so using now the Kepler third law, T square is proportional to RQ. Okay, here in this case should be KE. R is given like this. Now this condition geosynchronous. Now let's put the numbers here. G is this one, 4 pi square. Mass of the Earth is 10 to the 24. Now T here, to be geosynchronous, has to be 1 day. Okay. So how much it is, of course, has to be expressed in sec. And how much is 1 day in sec? It is 86,400 sec. Okay, so you just put the numbers and this one. So every geosynchronous satellite has to be located here. Okay, and of course the height should be 4.22 times 10 to the 7 minus RE, because it is measured from the Earth's surface. So this is so it is very far from the. It is actually much far high from the Earth's surface, because what is the radius of Earth's surface? Earth's surface is about 6,500 kilometer. It means order of 10 to 6, 6.5 times 10 to 6 meter. But this one is 10 to 7 meter. It has to be rocket very high. And the speed of the satellite is 3.07 times 10 to 6. If you just put the number here and you get this one. So it has to be. So in summary, if there is this is Earth geosynchronous satellite, it has to be located very high from the Earth's surface, and it has to move with this speed. Okay. Let's consider energy versus R diagram. Okay, so here this one goes like infinity, but we will not be concerned with this here. Anyhow, so G goes to 0 as R goes to infinity. The total energy now for an isolated system, this is conserved. Okay, and for here, when energy is less than 0, okay, the motion can only hold here. So you neglect some part of this. This is inside the Earth. Okay. So if the total energy is this, we know that the gravitational potential energy cannot be larger than total energy, because this one is always positive. So the motion can only happen in this region. Okay, and that motion is called bounded motion. When energy is less than 0, it is the motion has to be bounded. This is a simple result that the gravitational energy cannot be larger than the total energy. When E is larger than 0, you see, it can move, it can go to infinity. Okay, and that motion is unbounded. Okay, and this motion, according to Newton, can happen only in elliptic form, with the circle as its special case. Okay, and this motion was mentioned as parabolic motion or hyperbolic motion. Okay. So actually, we can prove that when E is less than 0, the system must be bounded, and we just illustrate this with one simple example of circle. Okay, circle is certainly, the circular motion is certainly a bounded motion. Okay, so let's calculate the total energy and see that it is actually less than 0. Okay, you can extend this to the general elliptic motion, but that's very technically complicated. So let's just consider circular motion. So now, first to calculate the total, remember total energy was what? Total energy was equal to 1/2 mv squared minus g r mm over g. So we are going to calculate this for a circular motion with radius r, and show that it is indeed negative. Okay. Now, for circular motion, let's first apply this centripetal acceleration, that gravitational attraction gives this centripetal acceleration. Okay. Since now we want to calculate 1 over mv squared here, you see you already have here mv squared. So you multiply both sides by 1/2 and transfer this into here, you get this one. Okay, so the kinetic energy is gmm over r, the magnitude of this just by half with positive. So the total energy is like gmm over 2r minus gmm over r, and the total energy is minus gmm over 2r. That is circular orbit. Okay, so this is negative. Now the smart student might imagine that for a elliptic motion, okay, with semi-major axis, which is also bounded, maybe this one for elliptic case goes like minus gmm over 2a. Okay, remember in the Kepler's third row, this r was replaced by a, and this is indeed correct. Okay, so that is the total energy of a elliptic motion, particle with elliptic motion. Okay, that is also negative. Okay, so this is for circular motion, negative. This is for elliptic motion, where a is the semi-major axis. So we have just I tried to explain that for a bounded motion for both circular and elliptic, okay, the total energy becomes negative, and that is in some sense definition of a bounded system. So this shows that the total energy must be negative for circular orbit, and also that is true for elliptic orbits. The kinetic energy of an object in a circular orbit is 1/2 of the magnitude of potential energy. Remember, the kinetic energy in a circular orbit, which is 1/2 mv squared, was equal to 1/2 of r over gmm with positive sign. Okay, and u was minus r over gmn. And if you add up this, the total energy is equal to 2r over gmm, gmm over 2 minus. Okay, so this is number. Actually, there is some meaning of this number, but let me not explain it. It's just half of the magnitude of the potential energy. Here again comes the statement I made that the elliptic orbit, you just replace this r by a. Okay, so that is the total energy, which is conserved quantity for the elliptic motion. And here a, the r, the radius is replaced with the semi-major axis. So let's go through some examples. Here, a space transportation vehicle releases a 470 kilogram communication satellite while in an orbit 208 kilometers above the Earth's surface. Okay, so when you calculate r here, you always have to add this radius of the Earth and times h. Rocket engine on the satellite boosts it into a geosynchronous orbit. Remember, the geosynchronous orbit is very far from here. So originally it was 280 kilometers height, but this rocket pushes this into the geosynchronous orbit. How much energy does the engine have to provide? Okay, so here you see that I think you have the intuition that where this problem must be solved with energy conservation. So calculate total energy here and calculate total energy here, and that the difference must be the answer. Okay, so let's see whether your intuition is correct. So let's go step by step. Now find the initial radius of satellite's orbit when it is still in its vehicle's cargo bay. So it is RE, okay, plus 100 kilometer, and that is 6.65 times 10 to 6 meter. So it's almost near the surface of the area. And then find the difference in energy for a satellite energy system with the satellite at the initial and the final. Remember, EF, total energy for a circular orbit, was minus 2, this one. Okay, remember this E, total energy for a circular orbit was minus 2 times R over GMM. Okay, so the final energy should be this one, and initial energy should be this one. It both have minus minus. It should be minus GME over M over 2 RF minus RE. Okay, so this information is given, RI is given, RF is the geosynchronous orbit radius, so you can just calculate it. You can just substitute the numbers and you can calculate. Okay, so that is substituting numerical numbers. You have delta E, which is minus 6.67 times 10 to the minus 11, and 5.97 times 10, and you need this much energy. Okay. Okay, so in chapter the latter parts of the chapter 11, we are going to talk about the atomic spectra and Bohr radius, Bohr theory of hydrogen. Okay, so a structural model can be used to describe a very small scale system. So what you mean by structural model is that when the scale is too high or too large or too small, so that you cannot directly observe it, then you will start with some assumption. For example, in handling the hydrogen, in approaching the hydrogen atom, you assume that there is a proton, and then there is a at the center there is a proton, and here is an electron. Okay, and you analyze this thing, for example, by light that is emitted in hydrogen atom. Okay, so the hydrogen atom is the only atomic system that can be solved exactly. Okay, so we are going to see that Bohr actually has solved this exactly, although that is a semi-classical result, that it coincides with exact quantum mechanical result. So in a sense, Bohr was very lucky that his semi-classical approach produced the exact result. Okay, and he was awarded Nobel Prize for this. So he was a lucky man, because he did not he did not give a full description in terms of quantum mechanics. His only semi-classical approach also reproduced the exact result somehow. Okay, and in particular, much of what is learned about hydrogen atom, which was only a single electron, can be extended to single electron ions such as helium or lithium. So this has many applications. So what you observe is that electromagnetic waves are emitted from the atoms somehow, and that can be used to investigate its structure and properties. Okay, but our eyes are sensitive to only visible light. Okay, and we can use the simplification model of a wave to describe this emission. Okay, so we are going to use a wave model of wave, which is light is a wave, and to describe this emission. Okay, so this is just basic fact. Actually, we are going to come back to this wave structure, wave theory in physics later, but here it's just give a very simple summary of what is wave. Okay, so wave has a very regular extension or a spread in space of this form, or sinusoidal form, and it is very regular and repeats itself. Okay, so it repeats itself, and the distance between this crest, okay, the crest to crest or trough to trough, is called wavelength of this wave, and the frequency is the how much it oscillates. Okay, it oscillates, how much it oscillates per unit time. Okay, and then of course the speed will be given by the distance it travels per second, and how much it oscillates per second. Okay, so c is equal to lambda f. So we'll come back to this, but let's just take this as a fact that the velocity, the speed of electromagnetic wave is wavelength times the frequency. Now, a discrete line spectrum is observed when a low pressure gas is subject to an electric discharge. Okay, so that is called emission spectroscopy. So basically what you do is that you have this cathode and anode, and you have a, let's just assume only one hydrogen atom. Okay, even though this is gas, let's just assume one electron. Okay, if you, I'm sorry, the hydrogen atom, and if you shoot an electron, okay, then there is some particular specific light with a given specific wavelength is emitted. Okay, not every wavelength is emitted, but if you, for example, bombard this hydrogen atom target with an electron, okay, then a very specific wavelength is emitted. Okay, if you bombard it with many electrons, with many diverse kinetic energy, then more lights will be emitted, but very specific wavelengths. It is not a continuous emission of wavelengths, but very specific wavelengths. Okay, so that is summarized in the emission spectroscopy. Okay, and the simplest line spectrum is, of course, that is for a hydrogen atom, which has more simple structure, proton and electron, and other atoms exhibit completely different spectra. So how does the spectra look like? It looks like this. For hydrogen, if you bombard hydrogen with some electron, only these wavelengths is emitted. For mercury, only this one. For neon, for only this one. Okay, and because no two elements have the same line spectrum, the phenomena represent a practical and sensitive technique method for identifying the elements present in unknown samples. So if you have some samples, if you bombard it with the electrons, and if you get this spectrum, then you can definitely say this is mercury or helium or hydrogen. The opposite is the absorption spectrum. Okay, so if you have hydrogen, I'm sorry, yeah, here. If you have hydrogen, and if you shed some light here, okay, so light means the light originally has, you can shine it with a continuous spectrum, but only specific wavelengths is observed. Okay, so if you shed a continuous a light with continuous wavelengths, okay, for a specific wavelengths, it is observed by the by this hydrogen. Okay, so that is called absorption spectrum. Okay, by passing white light means that it has all kinds of, all a variety range of wavelengths, but the observable spectrum consists of the light with a very specific wavelengths is observed by this hydrogen. That is called absorption spectrum. And in 1885, the scientist, physicist Varma found an empirical equation that correctly predicts the 4 visible emission lines of hydrogen. There are emission lines. Okay, so this one is emission spectroscopy. He identified 4 visible hydrogen. Okay, so H alpha line, the light with this nanometer 656.3 nanometer is observed, H beta and H gamma and H delta. Okay, so he observed this. He's the first physicist to observe the emission spectroscopy with these 4 specific wavelengths in the hydrogen atom. Okay. So here, for example, 410, what Balmer observed is this spectrum, this spectrum, this spectrum, and this spectrum. Okay. There are also, of course, more spectrums. And this is Balmer's empirical law, that he found out that this the four spectrum that he found can be put in this expression, and RH is the Rydberg constant. Actually, Balmer observed that, and Rydberg set out a formula for that. Okay, so here n is a 3, 4, 5, and 3, for example, corresponds to specific spectrum with wavelengths 4, 5. Okay, and that value is this one. So the spectral lines correspond to different values of n. Okay, of course, people didn't know this is this empirical law. People didn't know how theoretically you can derive this one. And then comes Bohr, provided the explanation of atomic spectra that includes some features of the current of the current accept theory is a full quantum theory. So Bohr's theory is not the full quantum theory, but it's I mentioned it's semi-classical. Okay, so but somehow it matches the exact result. Okay, so here the model includes both classical and non-classical ideas. So that is why it is called semi-classical. And his basic idea was this Planck's idea of quantization of energy levels. So I'll come back how he used this Planck's notion of quantization to this hydrogen atom and obtain the correct result. Okay, so Bohr theory structural model is very simple. Here is a proton with a charge plus, an electron minus, and the electron is orbiting here at some specific distance. Okay, and he assumed that electrons move in a circular orbit around the proton. Okay, and the force between them is of course the Coulomb force, Coulomb, which is Ke, Coulomb's constant, times E squared, a charge over R squared. So that is basically 1 over R squared. Gravitational force is Newton's constant times mm over R squared. Okay, so that is basically the same form, except that the mass is now replaced by the charge, and Newton's constant is replaced by the Coulomb constant. Okay, and he assumed that only certain electrons orbits are stable. So he assumed that here is a proton and only certain electron orbits are allowed. This is a kind of extension of the concept of quantization. Okay, so the orbit is not continuous. It admits only specific, for example, R1 and R2 and R3, and only these specific radius are allowed. Okay, so that is his assumption, borrowing the idea of quantization. Okay, so these are the orbits in which atoms does not emit energy in the form of electromagnetic radiation. It is stable and it does not emit any electromagnetic wave, the energy of the atom remains constant, and classical mechanics used to describe the electron's motion, and this represents claims that the centripetally accelerated electron does not emit energy and eventually spires into the nucleus, because the Bohr assumed that this one is stable, but according to classical theory of electromagnetics, if electron is accelerating, the accelerating charge always emit light, okay, and then it loses its energy and it has to fall into it, okay. So this is a catastrophe because there will be no stable electrons. But Bohr assumed that for these stable orbits, the electron, even though it is orbiting and accelerating, does not emit any electromagnetic wave for this very for a allowed orbits. Okay, that is Bohr's assumption. Of course, the full quantum theory explains that, but anyhow, we are just doing here a Bohr theory. Okay, so radiation is emitted by atom when the electron makes a transition from a more energetical initial state to a lower energy state. So I just said, as mentioned, that only certain orbits are allowed, and if the electron was here, this is proton, make a transition from the higher energy to lower energy, then electron is emitted. I mean, the light is emitted. Okay, and the frequency of the light follows exactly the Planck's law, where h is Planck constant. Okay, so the emitted energy, of course, is the difference between the electron energy at this orbit, and that from energy conservation, that is equal to HF, which is Planck's law of radiation. Okay, so that is the Bohr's idea. If the electron makes transition to a lower energy state, then the emitted light will exactly follow the Planck's law. Okay. And the size of the allowed electron orbit is determined by the condition imposed on the orbit's angular momentum. So there's one more ingredient. If this is the stable orbit that is allowed in Bohr's theory, what is the size of this allowed electron? Okay, and he assumed that the angular momentum of this orbit, which is equal to m, suppose it is rotating with v r, which r is equal to r times p, so lmv has to be quantized. Okay, so h bar here is h over 2 pi, where h is Planck's constant, and that is the Bohr's assumption. Okay, so the orbit which satisfies only these conditions are allowed. You see, since n is integer, r cannot be continuous, okay, because this is integer. Okay, so r satisfying these Bohr quantization conditions are the only orbits that are allowed. Okay. Okay. So here is what I've just said here. The angular momentum orbit has to satisfy this one. Okay, so that is the Bohr's orbit. And then the total energy is given by this. I don't have to rederive this thing because we know, if you recall that in Kepler theory, when the orbit is a circle with radius a, the energy was equal to what? Minus g mm, where this is m, this is m, over 2a, where a is the radius of it. Okay, so following exactly the same, you see that in the electric case, G is replaced by the Ke. The mass, product of mass, is each charge E squared, and the radius is given by this one. So in Bohr theory, if an electron is orbiting at a radius r, the total energy should equal to minus Ke E squared over 2r. I don't have to redrive it because this is just, you can take analogy from the gravitational case, and note, of course, the total energy is negative. It means it is bounded system. Okay, so I can use that. I can now derive this one. I'll just give a very brief re-derivation how this is arrived. Okay, so according to Bohr, you have m e electron r n Vn, which is angular momentum, has to be quantized, nh bar. And another equation is that since this one is orbiting, the centripetal forces, which is me Vn square over r n, suppose this is Rn, should equal to what? Coulomb force, Ke E square over Rn. Okay? So from this equation, you get Vn is equal to square root Ke E squared over me Rn. And if you put this thing into here, you get Rn, this equation. Okay, so if you, from this condition, you get Vn, and if you put just Vn into here, you get this one. Okay, so that is very simple algebra you can go through. And they show that the radii of the allowed orbit have discrete values. Okay, so n is discrete. These are all numbers. N is discrete, and they are all quantized. Okay, so that is what is meant by quantization. The orbit are quantized. Only radius r1, r2, which satisfies these conditions, are allowed in Bohr theory, r3, and it goes on because n goes on to infinity. Okay, especially the lowest radius here is what? When n is equal to 1. Okay, that is specifically called Bohr radius. Okay, and Bohr radius when n is equal to 1 is h bar squared me r squared, and if you just plug in the number here, what? H bar is equal to 6.6 times 10 to the minus 34. It's very small number, quantum number. The Coulomb constant in MKS unit is approximately 8.9 times 10 to the 9. We are using the MKS unit. The electron mass is approximately 9.1 times 10 to the minus 31 kilogram, and electron charge is 1.6 times 10 to the minus 19 coulomb. Okay, so if you just plug in this number, you get this. So it's order of 10 to the minus 8 centimeter. Okay, it is meter. 10 to the minus 9 meter is 10 to the minus 7 centimeter, and that is 0.5. So it's order of 10 to the minus 8 centimeter, which is what you call angstrom centimeter. Okay, so that is the orbit that has the lowest radius. Okay, least radius is called Bohr radius, and from here you see that Rn is equal to now n squared times a0, and the radius increases as n increases as the square of this integer. Okay, and En for an electron in an Rn, we call En is equal to minus 2 times Ke squared, and Rn is now what? Was what? N squared times A0. Okay, so it is given, the energy level is given by this one. And if you just plug in this number again, A0, then you get this one. Okay, so it's order of 13.6 electron volt. Okay, so as it at n increases, so the orbit, so this one is E1, which is minus 13.6. The energy level goes like this. Okay, so E2 is minus 13, of course, so it increases because this is minus. And the n is the quantum number that specifies the quantum state of the electron of the atomic system. Okay, so Bohr, as we have seen, the Bohr has derived this using the classical concept of these centripetal forces being equal to Coulomb forces, okay, attractive forces, and the idea of quantization, angular momentum quantization. But this one is somehow exact result, and it means that you can also obtain the same result using the quantum mechanics. So somehow this result, which is obtained semi-classically, coincides with full quantum mechanical result. That's why Bohr was a lucky man. He got Nobel Prize for this expression. Okay. So the lowest ground state energy is minus 13.6, and the first excited state energy is minus 3.4, and things goes on like that. So this is the energy level diagram. Okay, so the Balmer observed, what Balmer observed was this line, 4 lines. Okay, the four lines was transition from 3 to 2. Okay, and afterwards people discovered more lines. For example, this line, it goes from 3 to 2, 4 to 1, I'm sorry, 3 to 1, 4 to 1, 5 to 1. So Balmer, what Balmer found was the transition from the excited state to n is equal to 2. Okay, when the grounds, the lower states are n equals 3, it is called Paschen series. And of course, all the right wavelengths can be computed with this formula, n square of minus 13.6 approximate electron volt, n squared. Okay, so the quantum numbers are given on the left and energy is on the right. The uppermost level, of course, when n goes to infinity, it's 0, or its electron is removed from the atom. Okay, so it's the no binding energy. So the ionization energy is the energy needed to completely remove the electron from the ground state in the atom. So you have here a proton. Suppose this is in the ground state, n equal 1, it was minus 13.6 electron volt. So to tear this electron apart to infinity, you need this amount of energy. Okay, so the ionization energy for hydrogen atom is 13.6 electron volt. And the frequency using this formula, remember, E I minus E F is equal to N H bar. Okay, can be also calculated using the expression for EF. You don't have to use these numbers. Just remember EI is 1 over n squared times minus 13.6 electron volt. So numerically, you can always use this one. And wavelengths, which was equal to, remember, C is equal to lambda F. So 1 over lambda should equal to F over C. Okay, that can be also computed. And the wavelengths are found to be this formula here, like this. So if you plug in all the numbers, so 1 over lambda is precisely this RH. It's a value analysis experimenter of, you can put it into RH here. A readable constant. So Bohr, after successive explanation of all these emission and absorption spectra, extend this model for hydrogen to other elements in which all but one electron has been removed. So it means that the Bohr's atoms, if you have many nucleus, if you remove all the electron and if you have only one electron, then it can all explain very successfully this one. But if you have many electrons, it does not completely, it cannot accurately describe all the result. If you have more electrons, if you have only one electron, other electrons are all removed, then this result can always be applied. Bohr showed that many lines observed in Sun and several other stars could be used to, due to hydrogen. Okay, so it means that in the Sun and the other stars, hydrogen is the main component. They are correctly predicted by his theory if attributed to singly ionized helium. For example, helium has 4 electrons. If you remove all of the 3 and only 1 electron, then the Bohr theory can also be applied. So just a trivial example makes a transition from n is equal to 2 to n equal 1, 2 to 1. Okay, so 1 over lambda is 3 over h, and you get wavelength lambda, and the frequency is given by this. Okay, so I'll stop here, and I will come back with next week.